they're really the same thing. If one's messed up, so is the other.
That's an interesting
So is
take.
the other.
Well, in the roadmap, it's because that stuff is boiling. Like it changes because there's now something in the gaseous state, which wasn't before.
But it should all equilibrate into steady state, right? It's like if you have a set pressure on your roadmap.
But it's not like it can go backwards. Like
It depends. Yeah, it can go back.
I mean, as you go backwards in equilibrium, but
Right.
it can't like fill the entire space. Because some of it's down underneath.
What I'm saying is like the kinetics of evaporation of your like desired evaporation should only depend on three things: temperature, the like physical properties of that solvent, and the pressure. What else is it dependent on? The pressure of
Can we
the
adjust the camera again?
Right, I'm lumping that into like physical properties of the solvent. But none of those three things change if there's more solvent in your collecting class. But definitely, we've all observed this. So, classes as well. And like, you could say absolutely the same thing about the bio, right? There's more ice and then sometimes still plastic back, which
Hello?
totally.
You guys get your test back?
Yes.
It was pretty good. I mean, the vast majority of you did pretty well. What was the average? Like 150 or something? Yeah. So, I mean, if you did around 150, you're going to interview really well. We have an action-packed week this week. We've got 3 lectures. Sarah, you need some caffeine? No? Sure? Okay. We got 3 lectures, and then the sort of grand finale is Wednesday afternoon. Some people argue the greatest achievement in the history of medicinal chemistry. Maybe true, because I don't know if you count antibiotics as a lot of med chem, because they got the lead from nature. So some people, anyway, argue it's the best thing that ever happened. And
Can we adjust the camera?
one of the individuals that's responsible for the cure for HCV, Mike Sophia, will be here on Wednesday afternoon. And as usual, there's always a question from the guest speaker on the final. So extra incentive if you don't care about who helped invent the most important medicine ever. Like if that's not enough to get you to the seminar, then it'll also be on the test.
Can someone adjust the camera? Hello?
We still have 5 minutes. And today we have, I guess, 4 people that are supposed to be able to help us. So we have Purzols, or Elena and Lucas. Hopefully they're here. Yeah. Well, I don't see Lucas. So you're on your own. Oh, he's coming. Okay, great. And then for isoxazoles and isothiazoles, Teho and Han, where are they? Okay, there's Teho and Han is. So Teho, you're by yourself. But based on your tests, I think you can handle it just fine. Yeah. We have the front page of the handout. Is it on the screen? So, Lucas, you're going to be on the spot today with Elena. You know that, right? Okay. Great. I guess if everybody's here, maybe we can start 1 minute early. Vince, do you have your coffee?
I just got some.
Oh, okay.
Thank you.
Yeah, sure. Pyrazoles and isoxazoles. We're not going to cover isothiazoles today. That'll be tomorrow, as well as a bunch of bewildering case studies. Pyrazoles kind of important. Patrick, you make some pyrazoles over there? Yep, they make them. They make a lot of pyrazoles over there. In past years, we've had Pfizer folks, and every single time I ask them, they vigorously say yes. So these are pretty important little heterocycles, and the easiest way to think about making them is through cyclodehydration. So just imagining a 1,3-dicarbonyl, adding in either hydrazine or hydroxylamine, and the only thing you're going to have to worry about with this NOR-type cyclocondensation event is obviously regiochemistry. That's a problem. So if your hydrazine has an R group on it, we're going to have to think about where is the R group going to go. And if you use hydroxylamine, you have to think about where's the oxygen, where's the nitrogen. And we're going to talk about that a lot today. So that's the concern with NOR. However, if it's just a hydrazine by itself, you don't have to worry about that. Okay, the next way that's really, really popular to make these is through 1,3-dipolar cycloaddition. So your dipolarophile can be alkyne, and then you got the correct oxidation state. It can be an olefin, and then you just need to oxidize it up. Or you might want the paraxylene or isoxazolidine. And then your dipole can be one of a few things. It can be nitrile oxide, nitrile imine, or maybe even diazomethane. And there's a third type of dipole we'll talk about in just a second as part of problem today number 1. But maybe as a brief reminder, what's a fast way to make a nitrile oxide? There's a few ways to do it. Anybody make a nitrile oxide? No one has made a nitrile oxide. Okay.
Oxym NCS.
oxime plus NCS and a little bit of base will make that, which will then eliminate and give you nitrile oxide. Another way to do this people often use is take a nitro compound and a dehydrating agent. It will also give you a nitrile oxide. Nitrile imines we will talk about a little bit tomorrow in the context of apixaban. They're more rare, but can be made in a similar way. So you take, as you can imagine, a hydrazone instead of an oxime and do the same type of thing. But my very favorite way, the most dazzling way to make pyrazoles, has saved me multiple times, is this next one. Problem of the day number 1. So it's obvious that it's going to be either Elena or Lucas, or maybe the two of them together, as the champions of pyrazole chemistry. So where is problem of the day number 1? Oh, here it is. Okay. So do you folks want to take the iPad, or do you want to just tell me what to do? What would you prefer? You want to just tell me? Okay. Well, first let me copy what's going on here. Bless you. Okay, so while I'm drawing this first starting material, you can start speaking and tell me what you want me to do.
So you could form one free dipole that first step.
What's the sodium nitrate HCl do? Because I'm not seeing that.
Add on to the nitrogen. Form an NH bond.
Like that?
Sure.
Okay.
And then you'll
Do you agree with that, Elena? Okay.
you need to cyclize the carboxylic gas in the NO.
How do I do that? Maybe I need another step. Oh, acetic anhydride. So what's the acetic anhydride do?
That'll go on the oxygen of the NO, so you have a vegan group for cyclization. Basically,
Goes on the oxygen of the NL. What do you think about that, Elena?
So I think you're going to add onto the acid and then cyclize the other way.
Make a mixed anhydride? That looks really weird. There must be something wrong with this. Must be something wrong, right? No? Okay. That I guess is the question mark. So it is correct.
almost feels like we're in Australia.
Exactly. Discovered in Sydney. Sydnone. Okay, now we treat this thing with DMAD. And we do what, I guess what Lucas initially said. There's your product. Super powerful way of making pyrazoles. Everything okay?
I think it's actually, yeah, it's not the same as Rockdog, yeah.
You just do your product wrong. You're changing E for an R.
Oh, did I shift an R here?
You shifted it to the Sidnone.
Just swap an E for an R.
Oh.
No. The R group on nitrogen is on the wrong nitrogen relative to where it is in the handout.
Was it you guys that screwed up here?
Yes.
Aha! Never trust the TAs.
We are making problem sets now.
Yeah. No, what's drawn here is right, so that might have confused you.
Sorry.
Yes, it wasn't me. Okay, great. Actually, this lecture and next lecture are completely renovated from 2 years ago, so the TAs are not completely at fault. This is a new problem of the day, but luckily we got it right on the board here. Sidnone's super useful. I know they used to do them in La Jolla Pfizer all the time. Do you guys still do them over there?
Probably so.
Yeah. All right, let's take a look at the magical power of Sidnones to simplify the way you make certain types of pyrazoles. So, for example, how would you make this type of compound without using a Sidnone? Tejo, any thoughts on how to make this without no Sidnone?
How about 1,3-di?
Okay, sounds great. So if we use a 1,3-dicarbonyl, do you want to break this bond? Do you want to have like an internal hydrazine? What do you want to do? Before we make the 1,3-dicarbonyl, break this bond or keep it as part of a hydrazine?
Great.
Break ring B? Okay. Like that, correct? Okay. And then we gotta take something like that and treat it with hydrazine, correct? The Sidnone disconnection gets us to what starting material?
Probably.
Proline. Thank you, Max. Take proline, do palmolidate number 1 on it, then treat that with this alkyne, and you'll get major 10-to-1 that regioisomer as a product. You know, this is potentially okay, but you're going to have to navigate a lot of things here. You're going to have to first put maybe like an OTBS here, protect that. Then you're going to have to make this thing. Whereas you can buy this, it's free almost, and in sort of one pot, you're there. Same thing for this one. No Sidnones. How do you do it? Well, you might say, oh, I want to do a meoraborylation. First, we're going to brominate pyrazole, getting us back to, I guess we can do Tejo's disconnection again. How's that regiochemistry looking for you? Could be problematic, right? I don't know if the hydrazine's going to add in here first or here. You may get lucky, you may not. Probably won't be lucky. Probably give you the wrong regiochemistry.
What are the energetics of Sidnones? Are pretty stable?
Oh boy, I'm glad you asked that question. That was my next point. You can make Sidnones and you can run columns on them. Super stable. I love these compounds. You can do, if you have, let's say, the parent Sidnone where there's no R group here, where R is equal to H, and you have R prime whatever you want, you can lithiate those things. You can do iridium borylations, you can do brominations, you can do Suzuki's, whatever you want. And then at the end, do your dipolar cycle addition. So they're super happy stable compounds, unlike things like munchnones, which are usually in situ generated. Sidnones are super happy. They're mesionic heterocycles. In fact, mesionic heterocycles can even be used as, not drugs, but I've seen them used in agrochemicals before. So they're heterocycles that they're like zwitterions. Now look at the alternative. The alternative sidnone just starts from phenyl substituted glycine. And our alkyne is that. And the ratio is, I think, 5 to 2, favoring that one in the cycle addition, which for a med chemist is fine. So you take your glycine, you do the same as problem of day number 1. You make your sidnone, then heat it up with the corresponding B-pin alkyne. Weakly electron withdrawing by the B-pin gives you a slight excess of this one. Questions? Any confusion on sidnones? Super useful. Okay. The third major class of ways of making isoxazoles and pyrazoles is starting from oximes and hydrozones, as you can imagine. So that's this sort of retrosynthetic depiction here. And here are 3 tiny examples for you of how that works. So we can take this oxime, we can treat it with a couple equivalents of Uli, and then quench with DMF. And the product that we obtain is resulting from enolate attack here on DMF. And then once you get that, that's your product upon workup. That clear? How about this one? A lot of options for lithiated TMS acetylene adding into the alpha bromoxime you see here, followed by room temperature pot carb methanol treatment, and outpop something. What's the first step, you think?
SM2.
Sorry, Hannah, what do you say?
SM2.
All right, that looks good to me. Let's do that. That's our first step.
And then do nitron cycle addition.
We don't even necessarily need to do that. There's no nitrones in the building. We haven't added oxidant. We don't need to do that. What you can do with pot carb methanol instead, this is a very acidic position, as you can imagine. So this thing can isomerize, and then it can attack. To give you that. You don't like it, Hannah. You give me the look. No good?
I just don't think you need an oxidant to go through the nitron.
Where's the oxidant?
You don't need one to get to the nitron. It's just a tautomer.
But if I go to the nitrone, I would need to put some sort of group here.
Ah, I see. Okay.
So you either need an oxidant or you need an alkylating agent. And we have neither in the house here. So you can imagine it going to some sort of alenal intermediate and then cyclizing oxygen onto that carbon. And then if you continue to treat this and heat it up, the TMS will fall off eventually. So it's a good way of making the methyl isoxazole as well. And finally, what does this do? First step is Max.
It's just HWE.
All right, let's just do an HWE.
And I guess just the nitrogen is close down.
And then finally,
Just lost at the top.
Super. Okay, this top half of the board is about 1,000 papers. Summarized. No, probably underestimating that. Okay, great. Let's go through some case studies. So if we can get on the front of the board here, got it? Celebrex. Probably everybody in this room knows someone who uses, or maybe you have used it before. It's a standard pain reliever. This is the compound that had booming sales after Vioxx was taken off the market. We talked about the Vioxx disaster in lecture 1 or 2. So Elena, what's the way you're going to make this? That sounds pretty good to me. And the only thing you're going to have to address for us, Elena, is how you're going to get that kind of regioselectivity.
The carbonyl with the CF3s is more composition, so the nitrogen.
Does everybody hear what she said? Perfect. And so when you've got two highly differentiated carbonyl groups, you can rest assured you will get the proper regiochemical outcome. Great. How about this Dow insecticide, which is at the slightly lower oxidation state? So the paraxylene, how do you make the paraxylene there? Can we do 1,3-dicarbonyl again?
Kind of, but from the enone.
Kind of, but from the enone. Brilliant. You can either take acetylated hydrazine, or you can take hydrazine and then acetylate. And this will work via a Michael addition followed by cyclodehydration, sorry. Questions? Okay. We're going at a blistering pace here. So you folks are doing great. How about sildenafil? I mean, every heterocyclic class has got to have sildenafil. Let's think about the two ways of making this. So this strategy can never lead you wrong. I think the problem people have when they see these kinds of fused heterocycles is they try to think about the best route instead of just thinking about it in a very programmatic way, strategically disconnecting both sides, and don't think about which one is best yet. Now, you may know immediately. You may look at this and say, I know exactly what to do. That's great. Good for you. But not everybody does. So, Nick, which one do you want to start with?
So perhaps disconnect the B.
So we're going to start with A, and then we're going to make B onto that. And that will require some sort of X group here.
Make a hydrogen.
Is that what you want, Nick?
Potentially, yeah.
Okay. And we just have to figure out a way to make that. This is last week's lectures.
So disconnect the fragment with the two nitrogens.
And maybe we also want to defer that till later.
Yeah.
Let's say NBS. That one, correct?
Yep.
Now, before you make any judgments on this, you've drawn it out. It took you, I don't know, what, 20 seconds to draw that out? This gives you time to think when the interviewer asks you, how do you make that? You just draw that one out, don't think, and say, okay, now let's go the other way. So who wants to do the other one? What do you say, Tucker?
So we're gonna have kind of pull off the same something like aryl carboxylic acid equivalent on the they have an ester there and then amino at that position. Did it on 3-dicarbonyl?
Well, we got a 1,3-dicarbonyl potentially, but not yet. What are we going to do with this amine? It's in an obscure location. Can't really have a 1,3-dicarbonyl with the, with the NH2 there. So you have a couple options. You could put a nitro there, for example, in the 1,3-dicarbonyl. But since a pyrazole is sort of primed for nitration, you can just delete that. All right, and then we can do what Tucker just said. Oh, sorry, not phenyl, it's propyl. But you get the idea. All right, so we can take methyl hydrazine.
Well, I gave you the wrong methyl residue isomer.
Aha! Tell me about that, Saul. Let's talk about that. That's what I'm about to ask.
So the glyoxylate carbonyl is way more electron withdrawn, so it's going to add into that one first with the less sterically heteronegative.
So how do you solve a regiochemical problem like that?
Protect it with some other.
You could
Done
so
something else first.
a great idea. So one idea would be, buy the hydrazine with, or make the hydrazine with the NHCBZ or a Bach or whatever, and then that'll control your regiochemistry and then deprotect. So you can, one idea is do it stepwise. Another idea is defer the problem to someone else. What do I mean by that? Just mix with hydrazine. Now there's no regiochemical problem, is there? No, right? And what do we need to do to go from there to there, Saul?
N1 alkylation.
N1 alkylation. But how do I do that selectively? Maybe. I don't have a clue. So what I'm going to do is take an X-ray. Sorry, I keep changing that propyl to phenyl. I'm sorry about that. I'm going to take an X-ray of this. And when I take an X-ray, I'll save all the weighting. So in the X-ray, the dominant tautomeric form is actually this. So based on that, what would be your conditions for methylation? Based on lecture number 2 or 3? Tucker?
Neutral conditions, methyl iodide.
Brilliant. Because Tucker immediately looks at this molecule and he says, I don't see a pyrazole. He sees a pyridine, don't you?
Yeah.
Yep. So you just treat this with methyl iodide or dimethyl sulfate, whatever. It's going to dock itself on there, and you'll get 10-to-1 desired methylation. And the great thing is that the undesired regioisomer boils 40 degrees higher. So it's super easy to separate the undesired from the desired. Now here's another little interesting tidbit. If you use the right addition order, add this into this at a certain temperature, you can get 10-to-1 regiochemistry. If you add them 1-to-1 mixed and you don't play with your order of addition, it's 1-to-1. Right, how are you supposed to? Don't remember that. You can't remember that. But the point is, let's go back to the sort of interview or ideation stage, and you want to put something coherent on the board for your coworkers to understand. You just sketched out everything you need to think about. The top route is still possibly in play if you can deal with the sort of amidine regiochemistry issue, because you might have an issue there as well. And then you've got a halogenate, and then you got a regiochemistry issue here. This one seems more practical in the bottom, and indeed that's what they did. Sildenafil is a long story. There's actually a whole perspective written in OPRD about it, and as you can imagine, the generics have their own ways of doing it. A lot of ways you can make this compound. But these are the sort of main ways to think about it. Questions?
Why do you need an X-ray to determine what the dominant polymer that is? Can't you just use an MR?
You sure can, but when they're doing these things on huge scale, they already have hundreds of grams of the stuff, and it's just there. So it was a useful way for them to confirm that's what they had, and then back rationalize. But maybe they discovered this before even the X-ray. But this explains that selectivity. In general, that's a really good point, Hannah. In general, if you don't know your tautomer, you can check NMR, but you can also just use the trick we talked about in Lecture 3, which is just to take a pyrazole or an indazole or any of these, or an imidazole, and you treat it either under neutral conditions or with base. So you can imagine if we deprotonated this, now if we wanted a selective way to get methyl there, we could deprotonate. Right? So if you don't know, you don't have a clue, you can't tell the NMR is jumbly, just try the two conditions and see what you get. Base-free and neutral. Great. Other questions? Okay, great. Another way to make pyrazoles is through ring contraction. It's probably the only example we'll see today. It's a kind of rare way of doing it, but this is a cute one because it makes a very highly energetic compound as a result. And the mechanism is quite peculiar. And that's why it's a problem of the day. So, we need someone to volunteer for this problem of the day. How about Ziki? What do you say? Do you want the iPad?
Maybe.
Or you want to just tell me what to do? You'll have to speak really loud though, because my hearing is going bad.
Maybe the SAR. We also have the immune session, and then we can also attack the immune carbon.
Oh, you want to attack the imine carbon. I thought you were going to do another SNAR. That's clever. Okay, now what do I do?
So the anion on the nitro position with then go to the imine, then opens the ring.
I think what you're saying, I think if I got it right, maybe the better way to do this. Is that. And just correct me if I'm wrong here, Ziki. Now what?
The hydrosol, nitrogen will attack the nitrile.
That's pretty good. So let's just imagine the isomerization around this bond by tautomerization. And we're getting pretty close. Perfect. Awesome. You would never know. Ziki was just looking at her paper, paying no attention to me. Position of the methyl. No, position of methyl looks.
It's wrong in your penultimate intermediate. In the final.
Ziki, where did you screw up? Okay, let's go back here. Wrong here. So.
No, that one's right.
And we're going to add into the nitrile. So that's our nitrile carbon.
Oh, yeah, sorry. You just
And
yeah, you're good. Sorry.
are we good?
It's just upside down. Yeah, it's always crazy.
Haha. So are we going to issue a retraction to that? Never doubt Ziki.
So if it did another SNAR, that would...
If it did another SNR, it wouldn't. And so, the sort of trick of this problem is that the most electron deficient position is actually the imine and not the chloro. Perhaps due to, for the same reason that if you've got a 2,4,6 chloropyrimidine, you add in once at the 4, then you go to 2, then you go to 6. And that chloro position is actually not, when you add the first amine in there, the hydrazone, it's not as electron deficient as it used to be. So the more favorable, the more electron deficient carbon in that system is the imine. That's the trick of the problem. So if you go in and you add the hydrazine at that chloro position, you just won't get to the product. You won't get there. You could get there if you lose hydrazine out again, but that's going to be difficult. You could if you do that. You could eventually get there if you instead of having chloro here, had another hydrazine, and then just lost out another hydrazine. So in principle, if you were stuck and you drew that, it would get you to the product. All right, really quick, how about problem of the day number 3? Acomplia. I believe it's Acomplia. Where is that? The front page of the handout is Acomplia. And this was supposed to be the great white hope of Sanofi. For a few years, people thought this was going to save the company. It was for obesity, for libido, for depression. There was a long list of things it was supposed to be good for. They thought you should just add it to public drinking water and it would make the entire community happy. And then it turned out it caused suicide. Drug discovery is hard. So Elena, do you want to solve this problem in a microsecond? And what makes you so sure that the regiochemistry of that's going to be okay? Sorry, I couldn't hear any of that. Say it again?
The ketone with the ester off of it is much more electron
Yeah, super electron deficient. That thing is going to condense like crazy. It's going to give you the exact regiochemistry you want. So that's the very best way to make this compound. Awesome. How about this precursor to indoxacarb from DuPont? We've got a pyran connected to a pyrazoline. We see it, Max, too? What do you say?
Can the two methylenes be from formaldehyde? Sorry, that's like 2 steps back. But
Okay, that's great.
So
Tell me the immediate step back would be what?
would be just condensing with hydrazine.
Is that what you mean?
No, I meant acetyl, where the aldehyde is.
There is no. I see.
Or not acetyl, but there's an ester hanging off of that methyl. Sorry, I described it wrong. So it's
Draw the full ring system
sure.
like this.
Yeah, exactly.
Okay.
And then hydroxymethyl hanging off. And then to draw.
The issue is if you make this compound and then you add hydrazine to it, what do you think is going to happen?
Could close onto the ester too.
The first thing it's going to do is deformulate. So this should be a very unstable formal adduct. I think if we wanted to execute on your vision here, Max, we could take this compound, and the issue we would have is we don't want it to cyclize on the ester, so we would need to make this some sort of big old bulky protecting group or some sort, and then maybe cook that up with formaldehyde and have the thing close. Might work, but that's a bit of a pain. This alternative is what I thought you meant. You add this into hydrazine, you'll form the hydrazone. That then does a Michael addition and then a manic closure. And then the product you get out of that is this compound, which upon exposure to air, sitting around for a while, oxidizes out. How about this compound from Abbott? What ring system here do you think we should dissect entirely and with great speed? Sarah, what do you think? When you see this, do you want to get rid of B or get rid of A? You want to get rid of B, don't you?
Yeah.
Yep. So in a diaryl pyrazolone, the major tautomeric form of this thing is that. And so if we want to execute on what Sarah just said, we can use something like this. And the alkylation event can take place at oxygen selectively. And how do we close it up? Where are the Curie students? Elena, how do we close it up? You can do SNAR, but SNAR is kind of an unactivated position. So we need a transition metal or something. Can't hear you.
Palladium.
Yeah, you can use palladium, you can use copper, whatever your favorite one is. Ullmann, Buckwall, whatever. Solid-handed don't like that. That's okay. That's good. All right. I don't know. When you guys were looking at it, it's like, oh, okay, this guy has lost his mind, or oh, I agree. I don't know which one it means. Yeah. I don't know. Right? So
You've known me for 2 years. You can't tell those faces apart.
Yeah, you know, well, they sometimes are same. Yeah. It's usually the warning sign. It's like a check engine light. Okay, any questions? Oh, yeah, we have to make the perazolone. How do you make that?
It's like hydrazine.
Done. And that just comes from the ketone. Happy? We're good? Okay. Let's talk about indazoles. So what happens when you take a pyrazole and you benzanulate it? People hate it when you say benzopyrazole, right? Terrible. Just an indazole. Okay. Now, problem that number 4 is the most often used way of making indazoles. And it involves taking a annelid with an orthomethyl, and just usually people have an acetamide on there, but you can do it on a free aniline too. It works. Diazotizing followed by heat. What do you say there, Dongmin? You want the iPad, or you want to just tell me what to do?
I just talked through it.
You just talk through it? Okay.
So I think you'll form the nitroso species on the nitrogen first.
Okay, now what do I do?
Then you can imagine the amide nitrogen coming down and form the O minus, and the O minus will attack the carbonyl in the acetyl.
It'll attack the carbonyl in the what?
Acetyl.
Oh, you mean this O goes here?
Yeah.
I see. So we're just going to rearrange. This, correct? Okay, now what do I do?
You can just grab a proton from the acid.
That's going to give me something strange looking. That nitrine is what you wanted, Dongmin?
Yeah, kind of.
And there's your indazole. Most common way to make indazoles. Everybody good with this? Okay, remember it. We're going to see it again. Okay, let's take a look at this PDE4 inhibitor from Pfizer. Way before Patrick's time. We need some good disconnections here. Is there a candidate for a first bond you might want to eliminate? Tejo, any thoughts there? You want to alkylate here? Okay. Then what? So Tejo has helped us with our next disconnection of indosols. Let me ask you a question. Why are you using hydrazine? Why not just use cyclohexylhydrazine? Could we do that too, Tejo? Should be fine, right? Because the imine's going to form and then heat it up to higher temperature, and then you close it. So we can do it that way. Alkylating a cyclohexyl iodide or doing Mitsunobu, it's probably not going to be as good as just starting with the corresponding cyclohexyl hydrazone. Okay, great. Well, what else do? We still have this R group hanging off here for the ride. If I draw it this way, is there another bond you want to break? Vince? Like, what would be the most strategic bond to break so that you end up with two relatively equal pieces?
The R to the carbon.
Love it. Great. So what these folks did is they made the indazole, just like Tejo said, but they used cyclohexyl hydrazine. And then they took this dianion and added it in an SNAR fashion. Because this is kind of like, in this position here, it's kind of like a methyl ketone, right? Tucker, this is a pyridine, isn't it?
Yes.
Yep, looks just like a pyridine nitrogen. Power to it, kind of see like a ketone there. And so the whole starting material, they make this whole drug candidate from there. How do you like that? Pretty good. Acylate, do SNAR, selective hydrolysis, done. Right? Because these are differentiated now. That's very hindered. It's going to be hard to hydrolyze. This one's going to be easier to hydrolyze. Questions? How about this one from Abbott? Obesity candidate. First disconnection that's most simple. Tanner?
Probably the N-alkyl.
Brilliant. Love it. Just going to N-alkylate, end up with something like this. Put a nitro group there that we can get rid of. And using problem of the day number 4, done. Okay, interesting reactivity question to help us with as a great segue into the next topic is problem of the day number 5. So problem of the day number 5 looks like Saul has rigorously waved his hand to get it. You didn't see? He was like jumping up and down. So problem of the day number 5, that's the reported structure. So we need the reported structure mechanism, and then we also need what the alternative structure might be. Do you want the iPad?
Reported structure is just condensed to make amine and then oxygen and then nitrosazine.
You're going to have to help me with the oxidation state here, Saul. I think we're messed up.
You're just one low and you oxidize.
So what do I do to get to the right one?
Tautomerize a proton over from the exocyclic nitrogen over to the endocyclic nitrogen.
Okay. It's wrong. Reported structure. So what else can happen?
So the two options are the other heteroatom adds into that same amine, or the benzylamine condenses onto the nitroso.
Well, the other heteroatom into the would be like a four-member ring.
Right, yeah.
That's hard. Or what was your option two?
Condense benzylamine onto the nitroso.
And when I add into the nitroso, do I add an N or O?
You should add N.
So different nucleophiles add at different positions of nitrosos. In the case of an aryl nitroso with an amine, normally adds a nitrogen. But if you have an enolate, for instance, the nitroso can be attacked at oxygen. So let's follow what Saul says, and hopefully it gets us to the other structure. Okay, now what do I do?
Now the oxygen adds into the aldehyde.
And then what?
I lied. The nitrogen adds into the aldehyde are going to be on our way to an indazole. I think you're going to transfer that oxidation state over to lose water and make the indazolone.
That's the real structure. I think so. PDE4 inhibitor, number 2, shown in the top here. Now, later this week, we're going to have a lot of fun with triazoles and all sorts of bridging heterocycles will be coming. But as a preview to that, we will cover one such triazole here. Steve, what are your general thoughts on this ring system? Anything at all?
The amidine-like nitrogen or carbon between A and B kind of looks like a nitrile.
That's interesting. So, you said this is an amidine-like,
Yeah.
and adding a carbon into that nitrile is going to be difficult. But if we take that logic further, we've got an amidine. If we ignore this nitrogen completely, the way to make this would be through some sort of Robinson-Gabriel cyclization. So let's go with the amidine thought. And as we will see later on in a future lecture, such a thing can just lose water. Standard Robinson-Gabriel. And now look what has happened. POCl3, add in your hydrazone. Semi-carbazide is what they would call it. How do we make that? Now we're back. We've gotten over that uncharted territory. We're back in comfortable zone of how to make a purezol. Might need to put the board over there so I don't know if they can all see it perfectly. What do you want to do, Max? Just tell me.
We'll take the carbonyl to an ester and maybe use the purezol to attack like an aziridine and subsequent ring closure.
Like that? And then we need to make this. How do we make that?
That can just come from probably number 1. Or I guess not make carbonyl. Probably a little better.
How do we get regiochemical control?
I think it's kind of already there, right? Oh, wait, no, it's not. It's reversed.
I mean, you could use the same trick that we used with Tanner before. I think it was Tanner. On
2 stepwise.
yeah, putting some sort of protecting group here selectively, and then adding in, and then that's possible. Does everybody like that aziridine opening? It's kind of icky. You're gonna, I guess you'll metallate there and hope for the best. It might work. I mean, I can't say it's destined for failure, but what I will say is that this is also a very acidic position, so you'll have to do a halogen metal exchange and hope that you don't get any kind of deprotonation here. That may be an issue. But it's great that you did that, Max, because if we view these 2 ring systems as A and B, you did one of the disconnections for us already. So if we do the other disconnection, it would be something like that. And now when we add the hydrazine in, we get the perfect regiochemistry, don't we? Looks good. And treat that with base. They will cyclize. And you can leave it as a methoxy. If it's an OH, turn it to POCl3, put a chloro there. You've got a lot of options for what you're going to put there. And this is simple, just coming back from an amine and maybe an alcohol there. Alkylate, acylate, terbutoxide, and then add hydrazine in. Questions? Okay, super. We're doing great on time. Which leads us to our next problem, where we're going to take a deep dive into the world of medchem, not versus, just compared to radiochemistry. So let's take a deep look at this compound. I want you to ignore the pyran part. We're not going to talk about how to make a pyran. we got to think about that pyrrhizole. First, let's think about how the med chemists might have put this together. The med chemists are going to want to bring in the most convergent disconnection they can. Before we talk about radiochemistry, let's just think about that. So with the most convergent disconnection in hand, if we try to split this up into two equal pieces, what might those candidates be and what might the bond formation look like? Cheng, any thoughts?
I was thinking doing one three dipole.
Of what and what? Well, just tell me what the bond disconnection is.
Break the
So a 1,3 dipolar, I assume what you're saying is cut down the middle here?
yeah, kind of.
But before we do that, do you want to do all your transformations with all the spinach on there?
No.
Okay, so can you help me get rid of it all?
Yeah, just clean the benzene off first.
Okay, let's do that first. We'll worry about this pyran ketone another time. And we're just going to focus on that. And Cheng said 1,3 dipolar. Let's take a look at what that would look like. Something like this. And then treat that with NCS, let's say. Is that what you want, Cheng?
Basically.
Yeah. That looks good. I don't see anything wrong with that. And if somebody finds something wrong with it, it's Cheng's fault. No, that looks reasonable. Sure. What's another way to do this? Well, we learned, there's only 3 up there. So Elena taught us about the 1,3 dicarbonyl in a variety of instances, and maybe we can use that again here. There's our 1,3 dicarbonyl. When you treat the 1,3 dicarbonyl that's hiding there with hydrazine, the product you get out is this. There's ring strain associated with the 5,5, and so it doesn't dehydrate spontaneously. So when you treat this with methane sulfonochloride excess and base, you get out the product all the way here. So you get dehydration plus mesylation of the nitrogen. Now, as the astute members here might note that there are 2 possible regiochemical outcomes. And the major product is the desired regiochemical outcome. But we'll get back into regiochemistry in a moment. Okay, so now let's talk about the radiochemists. The radiochemists would have a hard time using Cheng's route because we would need to have a C14 label right there. Right? That's bad. But it's fine for medchem. Here's another obscure thing about radiochemistry that I guess you don't learn until you actually become a radiochemist. Is, let's imagine, I mean, the first thing you might say is, well, hey, Phil, why not just use the DMF, DMA labeled? Right? It's reasonable. When they did this reaction, with labeled DMF, DMA, no reaction. The reason for this is beyond the scope of this class. It's something you realize when you talk to radiochemists. Often they'll show you a route that MedChem or Process did. Then they'll show you the radio-labeled attempt. And for reasons they can't explain and nobody can, it doesn't work. Now, I don't know if it's the purity of the material they get from the vendor. Most likely not. But sometimes these C14 labeled materials just react differently with no explanation. Very rarely is it commented in the literature. In this case it is. But mostly it's one of these sort of hidden disasters of radiochemistry that they have to deal with. So they had to go back to the drawing board again. And instead of using DMF, DMA, they used formate. And so they were eventually able to arrive at their desired product with the caveat that the major impurity in this material was that, and they need that regioisomer. What do you imagine might be a way to equilibrate this wrong regioisomer to the correct one? Is there a way to do that you can conceive of?
Access methyl chloride.
What do you say, Cheng?
Just add more methyl chloride and some.
That's a great idea. I would try that. That doesn't work. But that's a great idea, because you can imagine mesyl chloride would then dock here, then maybe the chloro would add there, and then maybe thermodynamics would take over. It's a great idea. Certainly perfectly to propose that and try it out.
You scramble it with DMAP,
What would be the mechanism of that?
add in sulfur, and basically make the free pyrazole.
It's a great way to think. And maybe that would work. What they did was they treated it very similar to what Saul and Cheng are actually saying. They treated this with potassium terpetoxide because the process chemists actually knew this secret. When you take this and treat it with potassium terpetoxide, what's the only position you can deprotonate, or the first one you would deprotonate?
Methyl.
The methyl. And when we do that, we lose sulfene, and we get this mesionic anion. Which is floating around. And the two of these are cohabitating. And the sulfene is not super happy by itself. And the anion is not super happy by itself. But they obviously weren't too happy to begin with. So they decide to make a handshake. But this time, they shake hands at the thermodynamic position. So you can get a thermodynamic equilibration of this sulfonyl pyrazole to the right one. So a pretty deep dive into this interesting pyrazole. Questions? Okay, in the final 20 minutes or so, we have to talk about isoxazoles. And the first one is mycofungin. It's for fungus or some sort of thing, and they call it Fungard. I mean, there's so many jokes we could make about the name of this one. Most of them are not Title IX compliant. And so the best thing for me to do is just not make a joke about this compound. How do you like that? So let's take a look at this isoxazole. Medchem versus process. If you have to make 1 million analogs of this quickly, what do you think you would do from a Medchem standpoint? Cheng, you had a really good idea a moment ago. Do we want to use that one again?
I don't know whether it's applicable to this case.
What's that?
I'm not sure it's that applicable to this case, but yeah, sure, you can do that.
Yeah, that's what they did. Why not? Just do dipolar all day. That would end up with Ar alkyne plus Ar prime using Steve's method for making nitrones, or nitrile oxide, sorry. You take the oxime chlorinated in C2, it makes the nitrile oxide, it does the dipolar cycloaddition. Now, unfortunately, this sometimes gives regioisomers. And on large scale, they don't want to make a nitrile oxide. It's also a bit of a pain to make that alkyne, because you're going to need to use Sonogashira. So, do you have a alternative route? What do you say, Elena? Can we use the same? I know you're not on the isoxazole team. I know. But you've been telling me some good suggestions lately on pyrazoles, and I'm hoping we can use it again here.
Yeah, you can use a 1,3-dicarbonyl.
Let's do that. Let's use a 1,3-dicarbonyl. And let's this time maybe draw out the arrows. And while I'm drawing these, I need help understanding and rationalizing how to get the proper regiochemistry. Because hydroxylamine... So process took the 1,3-dicarbonyl. And do you think the regiochemistry will be right here? Some people say yes, some people say no. Tucker, you're vigorously saying yes. Why?
Because the left carbonyl is more electron poor.
Yeah, it's more delta plus. So for medchem purposes, the regiochemistry is good. But for process chemistry, no good. Because you get about, I think, 6-to-1 or something. Not good enough. So the sneaky thing about the process chemists is they first take this compound and they treat it with ammonium acetate under carefully buffered conditions. And then they found when they take this enamide, or vinylogous amide, and treat that with hydroxylamine, they get perfect regio control. So obviously I'm not asking you to memorize this kind of trick. The point is that if you're in a process group, you can draw this diketone out in the ideation phase, and then in the execution phase, you're going to have to do some empirical screening. I think the stroke of brilliance here is that if the hydroxylamine doesn't give you perfect regioselectivity, you think about a trans-enamine process. Emanation process. If you go through the imine tautomer. Questions? Okay. How about this factor 10A inhibitor from BMS? We're going to just make a disconnection here, not worry about this part, and just focus on this little pyrazole connected to a amino benzisoxazole. What do you say there, Gigi? You said you want to do a Buckwell coupling?
Yeah, just cleave to an aromatic part.
And can you tell me how you're going to get the right regiochemistry? I can go here or I can go here. And I'm also going to have probably have some sort of protecting group on this NH2, perhaps, to avoid, some sort of self-condensation.
Maybe just try 1,3-dicarbonate.
And what's the problem with the 1,3-dicarbonyl? Let's leave this as R right now. I don't want you to get distracted with the amino benzoisoxazole. You've got a phenylhydrazine plus the 1,3-dicarbonyl. What is the potential issue there? Regioselectivity is an issue. Sorry, nobody's catching me on that. There we go. Regioselectivity is a problem. So here's a sneaky, dirty trick that you can use to solve this problem of having two relatively similar electrophilic groups, where one of these is eventually going to be unveiled as an ester. Look at this. Now, your regiochemistry is perfect. Now, only this one gets attacked first, followed by cyclization. And then the furan is discombobulated with KMNO4. And there's no other offensive functional groups there. Now, all we have to do, you notice I put a placeholder here, is think about how do we forge that amino benzoisoxazole. What do we normally do when we see a carbon with an NH2 attached to it? That looks like a nitrile. So we can make this type of compound from that plus hydroxylamine. How do you like that? So the whole root, the R group here is a cyanofluoro. You make the hydrazine, you add it into here. You then take that compound, you treat it with hydroxylamine and high heat, and then you treat that with KMNO4. Okay, let's talk about risperidone. It's on the front page of your handout, and it can be disconnected into these two pieces. Tejo, how about the benzoisoxazole? That was quick. Done. All right, how about this one? Pyrimidinone. Well, we can do this if you want. That helps you. Hannah, any preferences on which one to start with? Either one is fine.
Intuitively, it feels like A, but I'm not sure.
So when you say intuitively it feels like A, what does that mean? Build A and then append B? Or build B and then make A?
Start with B and then make A.
Brilliant. Love it. And then when you're thinking about that, why did you say it was intuitive? Because what?
Mostly in this case because of the positioning of the heteroatoms, because it seems like that takes you back to reasonable starting materials.
And the reasonable starting material would resemble what in the case of this?
A 1,3-dicarbonyl and like
Oh, great. Love it. Awesome. Like this, right? Perfect. That's great. They don't do this. They do something very similar to what Hannah said. Okay, let's go through this slowly. You take 2-aminopyridine, you cook it up with that. The product of that is this. And, yeah, that's right. And as you can imagine, this should be reducible pretty easily. And so you can fully reduce this, and then chlorinate, and get out that. But you came up with that in like 30 seconds. Because you would go and see the amidine, you're like, the amidine on SciFinder, you can make it, but then you would think about it some more, and then you would realize, wait a minute, 2-aminopyridine is the same thing. Then you can reduce it. And in the final 7 minutes or less, how do we make this bizarre isoxazole? It's got not one, but 2 radiolabels. I have a C14 here and here. Not a figment of my imagination. Stuff from the literature. This one's tough.
Does acetone, both sides labeled, exist?
It can for you, Saul. What do you want to do?
I don't know. It just looks like all the things are in the right oxidation state at that point.
Let's do it. And then just see what happens. So we're going to buy C14 labeled acetone. Now what?
So there's going to be, so basically that accounts for the 2 C14 labels, and there's an equivalent of hydroxylamine, and then there's an equivalent of like formal pyrrolidine. Actually, prolidine is in the right oxidation state, sorry. This is prolidine and methylprolidine.
How do I get the right regiochemistry?
Maybe you make the oxime on acetones first and then do the cladocyanidation.
And you can all thank Saul for giving you back 3 or 4 minutes today. Straight out of the first board, we saw what was that, example 1 over there? From making 1,2-azoles from oximes. Awesome. Well, tomorrow is a nearly all brand new lecture because we saved so much time this semester. And you get 4 minutes back. And so we'll see you bright and early tomorrow.
store that here somewhere?
Oh yeah.
Oh,